Thank you for having me to talk today, and thank you for organising this. It's a little bit nerve-wracking going first. The first time I've spoken to an actual room full of people in a couple of years, but never mind. So I'm going to talk today about some work I've been doing on estimating the causal effects of the same exposure at multiple different time points in an individual's life course through multivariable Mendelian randomization. And I think one thing maybe I should be clear about right at the beginning is that when I talk about different time, I mean sort of different time in people's lives rather than different sort of time across the calendar. And I think sometimes I'm not always clear about that, so I just want to make sure that's clear now. So for those people who maybe don't work with MR so much, what we're doing in Mendelian randomization is using genetic variants to predict a value of the exposure that is sort of free from the confounding, and using that to estimate the causal effect of the exposure on the outcome. So what we're always really interested in is that causal effect of the exposure on the outcome. We're using the genetic variants in this case as a tool to sort of try and understand what that is. And there's three assumptions that are really key for that to be a sort of, to give you an estimate of the causal effect, which is that your instrument, the genetic variants, are actually associated with the exposure. That there's no actual confounders, there's nothing confounding those genetic variants and the outcomes that you're looking at. And there's no other pathway by which the genetic variant acts on the outcome that isn't through the exposure. So there's no like horizontal pleiotropy. Now, what if we're doing this with an exposure that varies across your life? So a typical example of a typical exposure we might consider for this would be BMI. Your BMI is not constant across your life course. I think sort of you can see that. If you think about, so this is some really great work by someone else I work with at Bristol, Tim Morris, who did looked at what is MR if your exposure varies across time, and showed that sort of MR estimates the lifetime effect of an exposure. We've discussed that for ages in the MR literature, but we've never really sort of sat down and gone like, but what does that really mean? And what it is we think in this is that it's the effect of the exposure on your outcome through all time points where the genetic variants affect the exposure. So if you're looking at BMI age 30 or BMI age 60 on your risk of having a heart attack, say, the genetic effect the effect you estimate with through MR would include the effect of the genetic variants on BMI age 50 that would, if that then had an effect on your risk of having a heart attack, and all other points. So it could be if it really mattered what your BMI was when you were 20. If the genetic variants you're using to predict that are associated with BMI when you're 60 are also associated with BMI when you're 20, you're going to be including that pathway in your causal effect that you're estimating. And if different genetic variants have different effects at different time points, that means it's not going to be the effect you estimate, it's not going to be the effect of having a unit higher BMI at all time points. If a unit higher BMI at age sort of 50 or 60 is associated with half a unit higher BMI when you're 20, that will be the effect that you're estimating. So you can't say it's the effect of having a unit higher BMI at all time points, it's the effect of having a BMI associated with having a unit higher BMI when you're 60 at all time points. But if we can do that, and with this interpretation, can we think about it in terms of a multivariable? Could we try and unpick the effect at different time points? And we can do that, well, I think we can do that using multivariable Mendelian randomization. Multivariable Mendelian randomization is MR, but including multiple exposures. And I always do it with 2. There's no reason that it has to be 2, it just makes the DAGs way simpler. We don't have to put any assumptions on the genetic variants being only associated with one period. You can take a set of genetic variants that are associated with one or more of the exposures and estimate the causal effect of each of those exposures. Multivariable MR does differ slightly from sort of standard MR in the sense that what you're estimating is slightly different because univariable MR, standard MR, estimates the total effect of the exposure on the outcome. And that would include any pathway through other exposures. Multivariable MR estimates the direct effect conditional on the other exposures that you've included. So not conditional on if there's something you've left out that mediates that pathway, that would still be included in the effect. But in this sort of second DAG, any effect, if exposure 1 had an effect on exposure 2, you would only estimate the effect of exposure 1 directly on the outcome that didn't go through exposure 2. And as with MR, there's a set of assumptions for multivariable MR. We need that, they're very similar. We need that the SNPs, or genetic variants, or IVs, whatever you want to call them, are associated with each exposure conditional on the other exposures. So you're saying, given that you've predicted X1, can we predict X2 with this set of genetic variants? That all of the SNPs or instruments are independent of any confounders or aren't confounded with the outcome, and that there's no pathway, none of them have a pleiotropic pathway to the outcome that doesn't go through at least one of the exposures included in the model. Doesn't have to be all of them, they don't have to be associated with every exposure, but any effect they have on the outcome has to go through at least one of those exposures. So if we, instead of thinking about just 2 exposures, what if those 2 exposures were BMI when you're 10 and BMI when you're 50? So how would we think about that and estimate it? So how we did this was we extended the model that was done in Tim Morris's work on univariable MR, and we thought about having, if we had 2 time periods, a module where the genetic variants for each time period come together to form this idea of a latent underlying exposure for that period that's genetically predicted. And that then is associated with your actual observed exposure, which will be affected by all sorts of things like by confounding, by measurement error, by the sort of day-to-day variation that you get in the like short-term fluctuations in the measure. So we think of that saying like your latent underlying level might be sort of your adult BMI or your sort of later childhood BMI. And it would, but your actual BMI is going to differ year on year slightly. And that wouldn't come into that particularly. We have multiple genetic variants. They together affect the latent period at each level at each period. They could affect multiple periods, they could affect one period. And we do need to sort of, an important thing, I think, important thing that we need to do is to include these in a multivariable MR estimation. You need to have separate genetic effects on each period. So you need to have that the genetic effects on your earlier period are different to the genetic effects on your later period, but they could be from the same SNPs. Maybe some SNPs all have an effect, but they have more of an effect in childhood, or they have more of an effect in adulthood. There needs to be sort of enough separation in the genetic effects of the 2 periods, but not complete, or it could be a completely separate set of SNPs, separate set of genetic variants, but I think that is sort of like much harder to believe biologically that you're going to have a completely separate, but they need to be sort of some separation. To show this, I did some simulations where I've just done 2 sets of simulations, one where we've got 2 latent periods to predict each exposure, and one where actually, so this might be BMI when you're 10 and BMI when you're 50, and then an idea where we've got 1 latent period, and that might be, say you were trying to estimate BMI when you're 40 and BMI when you're 50, and actually the genetic variants over that time period are actually exactly, are similar. Maybe, I don't know about the genetics of BMI in adulthood. I don't think anyone knows it that well yet, at that level, not that I've seen. And we can test this as well with a conditional F statistic, which is the same measure of a sort of standard F statistic you would look at in a univariable MR estimation, but accounts for that other exposure that's been included in the estimation. So this is sort of the model I set up. So I've got 2 latent periods that are 25% correlated genetically. X1 has a small effect on X2, and they both have an effect on the outcome. As you can see now, the total effect and the direct effect, the ones in red bubbles are the like true total effect and true direct effect for this model. And the total effect is slightly different to what you get if you try and work out those numbers. And that's because it includes the genetically predicted effect of the other time period as well as the pathway. So for X1, it's the effect on Y, so 0.2 plus 0.1 times 0.3, so the effect via X2. But it's also, you have to go back to L1, look at how correlated L1 is with L2 and include that effect, because if X1 goes up, L1's got to have gone up, and that's going to have increased L2. So that other pathway is also part of that total effect that you're estimating of the effect of X1 on Y. And if we do this with MR and multivariable MR, you see MR gives us sort of the true total causal effect, and multivariable MR gives us a good estimate of the true direct effect of each one. So there's very low bias. We've got really nice F statistics there, much bigger than 10, which is a sort of an approximation of a very well-grounded critical value for those. Now, if we have all I've done, this is exactly the same model, only now instead of there being 2 latent periods, there's 1. And now you see that we still get quite good estimates of the total effect. It's much higher because if X1 goes up, the total effect of increasing is much higher because all of the effect, X2 is going to have gone up by that much more as well. But the direct effect estimated through multivariable MR, which is the second column, sorry, it's lost its headings, but it's the second column, is more biased. It actually, sadly, in these simulations, because both of these have a positive effect, the actual bias evens out slightly because some of the simulations bias each exposure in the opposite direction. So what is actually much bigger that you see is the absolute bias across all of the simulations, which is how biased is it taken as an absolute level and then averaged, rather than how biased is it with the direction taken into account. And that is something I've seen that happens in any IV where you've got weak instruments in multivariable IV. I've seen that come up a lot. It's just a feature of the model. But you see we've got much smaller. The conditional F statistics really show you that you've got bias here. 1 is a tiny number. You definitely shouldn't be trying to estimate something with that. It's like really showing that you don't have any ability to predict the 2 exposures. Now, what if we left a period out? So up till now, I've thought about there being 2 periods and what are we estimating? What if we have sort of try and get closer to what might be sort of real life, and we had 3 time periods that were important for your outcome, but you've only included 2 of them in the estimation. You only have data on 2 of them, or you don't know what's important. So G is a set of genetic variants. We've now got 3 latent periods, but we're going to estimate it just as we did the other ones. So we're going to totally ignore the 3rd exposure. And I've set this up so we have L1 and L2, so the first 2 periods are correlated in the way they were before. L2 and L3 are correlated at the same level, and then there's also a sort of smaller correlation between your first time period and your later time period. So this could be sort of childhood BMI, middle adulthood BMI, late life BMI. Now, if we estimate, we've got correlated genetic effects here. Now, if we estimate, we see that our total effect is, again, we get the correct estimates and we get the correct estimate of the direct effect as I've marked it listed it on the screen here. But the direct effect of X1 and Y is no longer 0.2 as it was in the previous set. It's now still we're including that estimate through the excluded time period. So although you're getting a sort of unbiased estimate of the direct effect, it's not actually quite the direct effect. It's the direct effect including some of the effect through your later lifetime period. I should say the one thing I've assumed here is that Y is measured at or post X3. And so the estimate of the effect of X1 on Y is conditional on X2, the effect of the lifetime effect of increasing X1 at any point up, all points up to the time Y is measured. And you get the same with X2, that now you can see that on the sort of figure we get it's 0.3, but the direct effect I've written there is 0.37 because that's including the effect via the latest time period. And so now we've applied this to estimate the effect of child and adulthood BMI on smoking behaviour. So we took data from UK Biobank, and they measured lots and lots of things. But one thing they asked participants, very helpfully, was when you were 10 years old, compared to average, would you describe yourself as thinner, plumper, or about average? So we took this data and we GWASed it. I know it's not the greatest BMI measure, but this is a data set where we have some measure of childhood BMI in the same sample where we have adulthood BMI also measured. We then took adult BMI that was measured at the clinic and categorized it into 3 categories with a distribution to match the childhood BMI data we had, and GWASed both age points in UK Biobank. The caveats are that this was completely we haven't done anything about missing data, so it's European individuals with observations for both age points. Now this is the GWAS results. In yellow, I highlighted the SNPs that were sort of significantly more associated with childhood BMI, and in blue, the SNPs that were significantly more associated with adulthood BMI. So you can see we've got strong there are a number of signals that appear, and some of those do appear in both. They are sort of GWAS hits in both time periods, but they're much more associated with one than the other. So this is the data we're using to estimate the model. And in our univariable, just coming back to this, our univariable MR, we use childhood genetic variants to estimate the effect of childhood adiposity on smoking behaviour. And in the multivariable MR, we used child and adulthood hits to estimate the effect of childhood adiposity and adulthood adiposity on smoking behaviour. And I just took the latest big GWAS on smoking behaviour that I could exclude UK Biobank from, which had smoking initiation, so have you ever smoked? If you've smoked, have you quit? And if you haven't quit, how many cigarettes a day do you smoke? And these are the results we get. So the first column is the MR, so that is the total effect of each time point on the outcome. And the multivariable MR gives us the direct effect. As you see, we see a strong effect of age 10 BMI in the univariable MR, but that completely disappears in the multivariable MR. One question this raises is adult BMI is measured in late adulthood. This is UK Biobank. These guys are 50, 60-ish. Smoking is normally taken up when you're a teenager, and it's about 15, 16, 17, I think, in this data. So why do you think we see this effect? And we think it's because actually what we're doing is we're picking up genetic variants associated with adolescent adiposity and much more associated with adulthood adiposity, and that's what's driving the effects that we see. Thank you. And if there's time, I'll answer questions.
Thank you. That was really nice. Are there questions? Who's first? I saw your hand first.
Very interesting talk. I know that recently a study was published that actually looked directly at BMI across ages. Have you been able to test that hypothesis you just mentioned, that these variants that are affecting BMI later in life, in fact, are more likely, or in fact do affect variants earlier in life using this study, or do you have a plan to do that?
I would like to do that. I haven't. I think I know which study you refer to, though. If there's another one, it'd be great. But one issue with this is that power, in that this was UK Biobank, and we only have sort of just enough power to estimate the model. So we do need big data sets of different ages, and ideally sticking to comparing the same population, because I think comparing adults now to children now wouldn't, given the changes in the environment, and we know how sort of adiposity has changed over that time, that probably wouldn't be fair to put those both into the same estimation. But it would be great to do.
Two other hands over here.
Okay, thank you for a nice talk. It's great to have a talk in person again. I have a question about the assumptions. Can you tell us anything about how to check these assumptions, for example, especially the first one, which deals with the relationships of the different variables to one another?
So I didn't go into it at all, but we can use a conditional F statistic, which I sort of left out this talk. I'd be happy to talk about another time because that was previous work I did was in developing that. But it sort of looks at the association with one. It's a test, looks at the association of these SNPs with one exposure conditional on the other. And once you've done it, it looks very much like an F statistic. So you can apply the same sort of normal rules that you would do to that. And there are a few tests for heterogeneity and pleiotropy for multivariable MR, but they are still in development. I think that's an area which needs more research.
I'm going to say thank you very much, and I know there are other questions, but please save them for the coffee break because I'd like to not get further behind your time. And thank you again for wonderful. I'll do the same.
How do you put it on the full screen itself?
It's view.
Yeah.
Full screen.
Excellent.
So, hello everyone. My name is Sven. I'm going to talk about how to estimate age-specific marker effects for time-to-diagnosis traits. Now, the overall topic of today's talk are age-at-onset traits, and specifically we're trying to characterize, describe what is the relationship between genetics and age-at-onset traits. We could be interested in, for example, age at menopause, age at stroke, age at heart attack, or age at death. I mean, there are many more, given your diagnosis that you're interested in. Now, the reason why we're interested in age-at-onset traits is that we'd like to better characterize the genetic basis of diagnosis. And it has been shown that for many traits, age-at-onset could actually be way more informative about a diagnosis. And the thing we're specifically interested in today's talk is that can we understand the age-specific genetics behind age-at-onset traits that will allow us to conduct more accurate inference on those traits. Now, age-at-onset phenotypes require certain special care and attention, and this is because of censoring and truncation. Here I'm showing a dummy example of 20 random individuals, with blue indicating their lifespan from birth cohort 1930 to 1960. Now, if we conducted a study that lasted from 1980 to 2000, then by the end of the study, 8 people would still be alive, and we only observed the deaths of 9 individuals. And 3 people would have died already before they could have even entered the study. So we don't even know about their existence. So those properties are called right censoring and left truncation. And when we're analyzing age-at-onset phenotypes, we should be able to take those 2 properties into account properly. Now, the other feature of this talk was how can we characterize age-specific genetic effects? Now, imagine that you have a SNP effect that is varying in time, as in this plot over here. And if it's nice and linear, of course, it's possible to capture it with a simple linear model. Here, the Y is a continuous phenotype, and the SNP effect, we model it as it's varying across time linearly. However, if we decide not to take this into account, ignore this information that the SNP could vary in time, then we lose this information. And as you can see already in this plot, that the confidence interval is basically covers the 0 point all the time. It would result in, or ignoring this would result in inaccurate effect size estimates. We do not actually find this effect, and also reduce power. Now, if we now decide to model the SNP effect as a linear effect of age, then there are a number of questions that we can answer with this kind of model that are very interesting. Firstly, does SNP have a significant effect, at least at some stage in life? For this, we could check the point where there is the strongest evidence for an effect, where the confidence interval is the furthest away from the 0 point. Secondly, we could check, is the slope significantly different from 0? We could check the hypothesis, is beta 1 equal to 0? If we reject this hypothesis, then clearly there is an age-specific effect for this specific SNP. And lastly, we could even characterize at which ages does SNP show a significant effect. We could describe an interval at which SNP has an effect and at which points the effect disappears. However, for age-at-onset traits, it's actually not that simple. A few slides ago, I was showing the linear model for continuous phenotypes. However, if we would decide to use this kind of model for age-at-onset phenotypes, it would result in a misspecified model, because the phenotype now would be directly dependent on the covariates, and we could not estimate this kind of model. And the answer to, at least my answer, how to analyze this kind of data and estimate still age-specific effects, is to use Cox proportional hazard model with age-specific effects. Now, the key parameter of interest in this equation is the SNP effect size beta, and you see it's now dependent on time. Just as a reminder, for Cox proportional hazard model, the meaning or interpretation of the effect size could be that if you have some kind of baseline survival curve or baseline hazard, how much this baseline hazard or baseline survival curve is shifted given some kind of risk factor, in our case, genetic variant. In addition, we can estimate other parameters, such as genetic predictor of other chromosomes or PCs that you could plug into the model. Now, this approach enables us taking into account censored data, censored age-at-onset data. And as we're modeling SNP effect now as a function of time, this enables us modeling also and understanding the age-specific genetic effects. And in today's talk, we're going to assume that this effect size change is linear in age. I mentioned that we're going to use genetic predictors from other chromosomes. And the reason why we do this is you want to control for genetic effects, and thus increase power, similarly to other genome-wide models are doing, such as BoltLMM, FastGeo, or Regini. As a first step, we're using BSW model that can jointly estimate the genetic effects for age-at-onset traits. It has been shown to have a good predictive performance. And then using this whole genome jointly estimated model, at each SNP, we can adjust the Cox proportional hazard model for the BSW genetic predictor and use this kind of Lee one-out chromosome approach. So basically what we do, if we want to estimate effects in chromosome 1, we're going to take the genetic predictor on all other chromosomes, except the first one, and we're going to test each SNP in that chromosome with that particular adjustment. Then if we move on to the next chromosome, then we take the genetic predictor using all other chromosomes, except the second one, and we're going to test each of the SNP with that adjustment. And then we can move through the genotype like this. Now, a few words about significance testing. As you now can see, instead of one parameter per SNP per test, now we will have 2. And at each age, we can construct the following test statistic, a chi-squared test statistic, that's simply a ratio of the effect size squared divided by the variance estimate. And now it can be shown that given the null hypothesis of no effect at all, it is sufficient to use chi-squared distribution with degrees of freedom of 2 quantile for significance testing at each age simultaneously. So we can use this test statistic, but now we should simply use chi-squared with degrees of freedom of 2. And in parallel, if we had only one parameter, we could use the same test statistic, but with degrees of freedom of 1. So that matches very well. Now, we want to use all this theory to analyze age at menopause in UK Biobank and the Estonian Biobank. So we analyzed 8.4 million SNPs, and we estimate the SNP effects as this changing linearly in time. Each analysis was adjusted for BSW Lee one-out chromosome predictor for age at menopause. In UK Biobank, we can use 175,000 women, out of which 127,000 are known and 48,000 are censored. In Estonia Biobank, there are 70,000 women, out of which 23,000 are no menopauses, so the power is slightly lower there. And we're going to focus only on the replicated associations that, that we find in the UK Biobank and what we also replicate in the Estonia Biobank. Now, to go back to the questions I presented in the beginning, first question was how many SNPs have a significant effect, at least at some stage in life? We tested the significance at the age where the test statistic, chi-square, is the highest. And we arrive at this kind of these kind of results, where the blue dots indicate the novel discoveries, novel meaning that we discovered them both in UK and in Estonia. And in summary, we replicate 249 previous associations and we find 25 novel associations with this kind of model, indicating that 9% of the discoveries are previously unreported. Thus, this more complex model gets a slight increase in power. Now I'd like to focus or give an example of two loci that turn out to be novel in chromosomes 11 and 15. For example, the SNP in chromosome 11, we find it's downstream of spin duct gene. There has been previously suggestive, but not genome-wide significant association with age of menarche. And now we can see that there is a slight increase of menopause risk with age. And similarly, there is a SNP in chromosome 15 upstream of USB3 gene, and previously again there has been a suggestive association with age of menopause, and now we see that this menopause delaying effect disappears as we approach age 55. Now the second question was how many SNPs show an age-specific effect, and we're going to test the hypothesis beta 1, is it equal to 0, beta 1. And out of those 274 SNPs that we previously found significant, we now find that 18 of those exhibit a slope, meaning that they truly vary across time, indicating that at least 7% of the menopause effect change across ages. We managed to also replicate these discoveries in Estonia. However, we see that there are also 41 that do have an effect in UK Biobank, but they did not replicate in Estonia, so there could be potential evidence for maybe even 22% of menopause effect changing in time. And out of those 18 that we find that have a slope significantly, only one of them are among the previously 25 discovered, meaning that the known loci for menopause mostly, the known loci mostly can often be time varying. That's my point. And if we now zoom in to those 18 significant slopes, the common or overall trend is that the effect size that could be pretty strong in earlier ages, age 40, age 45, it gradually disappears for all of those 18 slopes, basically, and often the genetic effect for menopause completely disappears by age 55. And lastly, at which ages the SNPs show a significant effect? Here we evaluated this chi-square statistic at ages 41 to 55 on a grid. At each age, we checked, does the chi-square statistic give a significant result? We checked how many SNPs remain significant throughout different ages. And at each age, we tried to replicate the analysis in Estonia. So here, first we tested the effect size at age 41. And we see that we get almost 60 SNPs that are significant at age 41. Now, if we check age 43, we see that by age 43, slightly smaller number of SNPs are still significant, but we get an additional number of SNPs that turn out to be significant by age 43. We can continue this procedure, seeing that the number of significant SNPs that were significant at age 41 continues to decrease while we get new effects becoming significant in later ages. And the full picture looks like this. And we see that there is a slope, there's a peak at age 49, and following this peak, we see a very rapid decrease in the number of effects. Some key points that I'd like to point out here is that at age 47, only half of the effects that are significant were also significant at age 41. So actually, we get quite an increase in the significance of the effect. And in addition, what is interesting is that we find a substantial drop in the number of significant effects after age 53. We kind of saw the same effect already with the slopes, but here is another verification that it seems that the genetic effects decrease in later ages. So in conclusion, here we have proposed to analyze age-at-onset phenotypes with age-specific Cox proportional hazard model. We find 25 novel, roughly 9% of them, of all discoveries, and we also replicate previously known regions for age at menopause. The model detects regions that have changing effect across ages. We managed to find 18 of those that show a changing effect. And lastly, we can also pinpoint the ages at which the effect is the strongest. We find that at age 49, we find the most statistical evidence for genetic effects. So with this, I'd like to thank you very much for your attention. And if you have any questions, I'm happy to answer them. Thank you very much.
Thank you. That was also very interesting. Are there questions? Yes. Can you wait for the microphone? Then the remote. Sorry.
Hi, I'm Jerome Breen, King's College London. Thanks for the talk. It looks really interesting. I just wondered how you adjusted for power at the different ages, because presumably the numbers of women peak at certain points. And I wonder if that happens to be at 49.
I mean, the nice thing here is that actually we have just one analysis. Like this Cox model, we can just put like all women together and specifying that the effect size has to change throughout time. Basically, like everything is just combined in this one analysis already.
So if you have a much larger number of women with experiencing menopause at 48, 49 than at, let's say, at 55, how does it solve that problem?
I personally think that it's not that big of an issue. I mean, like given that the women are unrelated, roughly, then basically it's the same question as.
Well, see, it's power to discover genetic variants because your sample sizes. Maybe I'm misunderstanding the issue. That it's going down.
So is it when you said you've got more significant effects at age 49 and 55? Does that reflect that you've got more events at age 49 and 55?
Yeah, I'm not entirely sure that we can say this, that like if you have more events at 49, it will like clearly decrease or increase the power at age 49. In then I think we should still look the model as a whole. So I mean, this requires like more research to understand like how exactly like the power is implicated. I would guess that actually there are so many menopause cases in the center already that we probably need to control the edges better. So you could specify the slope, because I could guess that this slope might vary quite a lot given like the edge cases at 40 or 55.
Thank you.
John, no, please wait for the mic.
It was essentially the same question, and I was just going to suggest you look at the confidence interval of your estimates and understand how those change with time. And I think you'd be better off focusing on estimation than the number significant at time points as well. That might be easier to interpret.
Mm-hmm.
Thanks. Yeah, I didn't quite understand your first test for whether a variant has a significant effect at any age. Does that not involve? So you've got the chi-square function as a chi-square variable as a function of time.
Yeah.
Are you testing like you're looking at every single time? Doesn't that introduce?
Yeah, I mean, like basically 1 and 3 are kind of overlapping. It's just that 1, I'm simply checking the point where it's really the highest, where we truly have the maximum evidence for an effect.
So what's the null distribution of that?
The null distribution that there is no effect. That beta 0 and beta 1 are equal to 0.
Okay, so it's very similar to your slope tests.
Yeah.
Yeah, I see.
Yeah.
Okay.
We also have a question on Zoom from Stefan. Stefan, are you able to please unmute yourself and ask your question?
Can you hear me?
Okay, I will read out the question. So using the linear time trend, don't you introduce bias? The linear trend has to be forced towards 0 as you move closer to maximal event times. Does that make sense?
Yeah, I agree. I mean, in the end, we're still using a linear model. It's a complete simplification, and I've tried other models. I've tried using an exponential decay model there. I've tried also like different slopes, different thresholds simply. However, it seems that in my initial test, the linear model gave the highest likelihood for this kind of models. But of course, I think we should be very cautious. How much do we interpret this? I mean, I could extend this linear line until 70 or the early 20s, but I'm specifically keeping the range here between 40 and 55 just to avoid misinterpretation.
Let's go.
Thank you, very nice talk. Just a quick question in case I misunderstood. So are you analyzing, you said you are using the Cox proportional hazards model here. So are you analyzing the data as a prospective cohort? So are you considering basically kind of the follow-up time only from the time of entering the study up to the last follow-up? So kind of what counts as events in your analysis?
So basically, I mean, here I didn't take into account the left truncation, meaning that at which time point you're entering the UK Biobank cohort, and then the event is simply the time when the woman has self-reported the age of menopause. Or I'm not sure, did I answer your question correctly?
If not, we'll have to leave it.
Okay. Okay.
I'm going to move on because we're going to try it. Thank you very much.
Thank you very much.
Going to try to have an online talk now from Vasileios.
Hello, can you hear me?
Yes, we can't see your slides.
Hopefully that will work. Can you see my screen?
Yes.
Oh, that's great. Good morning, everyone. I will be presenting to you some work that we've been undertaking with regards to pleiotropy robustness in Mendelian randomization by means of using a sex interaction. As previously outlined by Eleanor Sanderson, the framework of OMAR is essentially using a set of genetic variants in order to predict an exposure of interest denoted X. And by this way, we are avoiding the confounder, the environmental confounder U. This is, of course, subject to a certain set of Ivy core assumptions. These are instrument strength, that is, the genetic variants have to be explaining an amount of variance in the exposure X. Secondly, the genetic variants that we use as instruments should not have a direct effect on the confounder U. Thirdly, and crucially for our purpose of methods development for this particular goal, there should not be a direct effect of the genetic variants on the outcome Y, other than through the exposure X. The way that sex interactions have been used for Mendelian randomization dates back to 2008, when Lina Chen and co-authors performed a sensitivity analysis for investigating the effect of alcohol on hypertension, stratifying by sex. What they did was that, apart from the influence on enzymatic breakdown of a particular variant of ALDH2 and how this affects alcohol, in traditional societies, there was also shared societal pressures and so on with regards to women consuming alcohol. And the authors took advantage of this by checking how genetic variants for ALDH2 associated with hypertension. This way, any residual significance of this pathway would indicate potentially pleiotropic mechanisms, that is, ALDH2 variants affecting hypertension in pathways other than through alcohol. And this was consistent with the null and interpreted as evidence for no pleiotropy. therefore putting more trust in the male-only analysis, for which the data looks a bit like that. Westpiller and co-authors in 2020 systematically treated this approach and developed the MRGXC method, in which the first stage model of the two-stage least squares analysis includes an interaction term. That is, the exposure is predicted both by the genetic variant as well as the interaction term. And they showcase this, they use the BMI GRS that appear to be stronger for higher TDI, that is for higher material deprivation. Another method that is related with regards to interaction variables is the MR Genius by Erik and authors, in which the instrument G is a valid instrument for the mean exposure levels as well as for the variance of the exposure, assuming that there is an interaction there. This holds if there is an interaction. However, a crucial advantage of this method is that there is no need to have prior knowledge on what the interaction is, so we do not need to specify this. The authors also note that there is a case for potentially magnifying weak instrument issues with this approach. We're focusing on sexual dimorphism and sex as an interaction variable because it is temporally preceding most commonly used phenotypes in epidemiology. Therefore, in a causal inference framework, it is less likely to be a mediator or a collider, unlike an interaction term such as TDI, which comes later in life and issues in inference could arise. An example of a phenotype that is highly sexually dimorphic and could fit our purpose of investigation is waist-to-hip ratio, which in a recent meta-analysis of up to 700,000 individuals, approximately 1/3 of all genetic signals were found to be sexually dimorphic. That is, associated in a differential manner in men and women. What we're assuming that the genetic mechanism to be in such a case is that apart from the direct effect of the genetic variants on the exposure X, say waist-to-hip ratio, there is also for one level of the interaction of the binary interaction variable, that is sex, an additional effect through this interaction pathway. This is symbolized by the capital delta here, and we see that when S equals 0, this is directly 0, so there is only the effect of the genetic variants. We also generate the outcome in the further simulation studies with a view to purposefully make biased the two-stage least squares and the IVW methods, that is with pleiotropy. This pleiotropic pathway is here denoted as alpha, and it reflects a direct effect of G on Y. What is more, we are also making this alpha effect correlated with instrument strength, which is referred to as the inside assumption or orthogonality assumption in TMR literature. This would make two-stage least squares and IVW methods in MR biased. The way that the binary interaction variable would come in handy in this case is that if we take summary statistics per stratum of sex, we see that the expected values are as such. So for level 1 of S, we have gamma plus capital delta. That is the interaction effect. For level 0, we have just gamma. And similarly for the SNP outcome associations, denoted capital gamma, they are as such. Then when we estimate the difference in strata and we meta-analyze this, the differences as opposed to the SNP exposure and SNP outcome associations per se, we say that alpha J is cancelled out exactly, and it appears that in principle the causal estimate beta is accurately estimated. This is slightly different than modeling heterogeneity due to pleiotropy, which is being performed in MR regular MR median, as it's exactly cancelled out, assuming that it's constant across sexes. Of course, this may not always be the case. The other issue at hand is taking into account weak instrument effects on the analysis as potentially were genetically proximate interaction, for which we may be having much less strong interaction as opposed to the sheer association with the phenotype. We're quantifying this with the stratified F statistic, which is essentially the difference in the sex-specific estimate squared over the variance. And we show that this is very similar to an F statistic and exerts the same amount of regression dilution as that of the F statistic. And anticipating much weaker interactions as opposed to strengths of association, we embarked on using MR RAPS, which is by King-Hyun Zhao in 2021, and it's a way to allow for measurement error and heterogeneity. And this is in difference with the IVW method, which does not allow for measurement error. And another part of MRAPS that provides benefits for estimation in this case is that it also simultaneously allows for heterogeneity. But what would heterogeneity look like in such a model? So heterogeneity would be sex specificity both for the exposure and sex specificity both for the outcome of our instruments. And by jointly estimating beta and tau squared, the MRAPS model provides theoretical benefits for such a scenario. However, we also show that there is an additional assumption that we have to make in order for the estimates to be valid. And we refer to this as the insight to assumption. The two-sample MR framework, in which we have completely separate exposure measurement and outcome measurement, is not particularly problematic, and the approach is as described above. For one sample MR, we're making an additional in which the error terms for the SNP exposure and the SNP outcome associations would be correlated. We're making an additional amendment based on the 2021 paper of Barry and co-authors, in which they are using an alternate extraction for the SNP outcome associations, termed the collider correction. And this is based on artificially inducing collider bias in the SNP outcome summary statistics generation, and then correcting for it. We're using a very similar approach, just separated in two stages and stratifying by sex. Moving on to some simulation results. In the two-sample framework, we're purposefully invalidating the analysis by having this insight assumption violation of MR, and we see that both IVW and MRAPS methods are asymptotically biased, and both methods that are leveraging the sex interaction and analyzing as previously described, denoted IVW strat and RAP strat, are both asymptotically unbiased. However, the weak instrument robust RAP strat method is achieving lower bias and nominal coverage at much lower strengths of the interaction, denoted here by the F strat axis. We see also that type 1 error is well controlled and power as well. For one sample MR, we also have an additional comparator of the MR-GXC approach. The MR-GXC approach and the stratified RAPS method with the collider correction amendment are both asymptotically unbiased. However, we see that the collider correction and stratification method are similar to the two-sample MR simulation results, reporting lower bias at lower strengths of interaction. Similarly for coverage, both methods achieve nominal coverage. However, coverage is looking better for lower strengths of interaction. When we're moving to scenarios of heterogeneity, that is sex specificity of the variance for both the exposure and for the outcome, we're discriminating between the random effects model, the fixed effects model, and a choice between the two based on a heterogeneity statistic in the bottom right panel. Firstly, we see that we are able to detect well when there is heterogeneity, and when we are applying a random effects model based on this Q statistic Q, the estimates are asymptotically unbiased. However, when we are generating data under what we refer to as the inside 2 violation, all methods are essentially breaking down, so this is something to keep in mind. Moving on to the applied analysis in the effects of waist-to-hip ratio on a range of, to begin with, binary outcomes. We're using, for external selection, the giant consortium results for waist-to-hip ratio, in which 49 SNPs were genome-wide significant. Of these, sex specificity was widespread, and we're analyzing in UK Biobank in order to avoid winner scares. So what appears to be the case is that in two-stage least squares analysis, there appears to be an effect of waist-to-hip ratio on type 2 diabetes, myocardial infarction, and this does not persist in the sex-stratified methods. Conversely, the two-stage least squares does not indicate a significant association of waist-to-hip ratio with heart valve disease in the rightmost part of the plot. However, both the stratified MR methods are indicating a negative association of waist-to-hip ratio with heart valve disease. Moving on to the continuous outcomes, we note a paradoxical negative association of waist-to-hip ratio with height as well as BMI, which, if we were to take at face value, we might have interpreted as a negative sort of a protective causal effect of waist-to-hip ratio on height or on BMI. And this does not pertain in the stratified analysis, where we are identifying estimating associations that also are consistent with null in both height and BMI. However, the effects of waist-to-hip ratio on serum lipids in, say, HDL and LDL and blood pressure measurements, although the measured effects are lower in magnitude, they also pertain in the stratified analysis. What I'm not showing in this plot, but what also was the case, was that they survived multiplicity corrections. Overall, the pleiotropy is a major concern when undertaking MR analysis, and there should always be taken care. And one way of doing this is with data-driven approaches, such as MR-Anchor or MR-Median, a host of other very effective data-driven ways. And when we have access to variants that differentially associate with the exposure across sexes, it appears that such an approach could improve estimation. It does not come assumption-free. We still have to make the inside 2 assumption, that is, we have to assume that the sex specificity of the pleiotropic pathway is independent of the sex specificity of the exposure for the variants. We provide a way to do this with a heterogeneity statistic. And if a fixed effects model is chosen, then the analysis is relatively more robust. However, if a random effects model is chosen, we'll have to be transparent about making this assumption, which was the case in a lot of continuous outcomes in our applied analysis. And in the applied results, it appears that the effects of waste-to-heat ratio on type 2 diabetes and myocardial infarction, as estimated by this method, might not persist and might be due, we hypothesize, to BMI pleiotropy. Finally, practical limitation is that while in principle this can work with two-sample MR, public figures availability is limited with regards to sex-specific results, so this could impose some limitations on the analysis. Thank you very much for your attention. I'd be happy to discuss any questions or comments.
Thank you very much, Vasileios. I think we have time for exactly one question. I was going to jump in. Go on. No, you go. You go.
Thank you. It was just a quick clarification. Sorry if I missed this. So this would be applicable in a setting where you thought there was different genetic architecture of the exposure by, for example, gender, but you thought the kind of causal relationship from exposure to outcome is the same across both genders. Is that right?
Yes, this would be the ideal scenario where we have a homogeneity across genders for the outcome and some discrimination for sex for the exposure. And this would lead to a fixed effects model, in this case being chosen. However, a lot of care should be taken because it doesn't feel completely realistic to assume no sex specificity for the outcome. And this is when a random effects model could be prioritized. I don't know, does that make sense? Would that answer your question?
Thank you. I had the same question. All right. Thank you very much, Vasileios, and thank you for being our first remote speaker.
Thank you very much.
And the last speaker in this section is Samvida, who is definitely here. Yes. If I can bring up your. I think that's you. Okay. You probably know how to make your screen. So you've got 2 minutes, 20 minutes. Finish by 2 minutes.
I can see my slides, but I don't think.
Yeah, I think it's locked.
Okay, excellent. Thank you for bearing with that. Hi everyone, my name is Samvida. I'm a PhD student at the University of Oxford, co-supervised by Professor Cecilia Lindgren and Professor Chris Holmes. And I'm excited to talk to you today about one of my PhD projects on the genetic architecture of longitudinal obesity trajectories in primary care electronic health records. So to start with some background on the genetics of obesity, obesity is defined as the accumulation of excess body fat and is a growing global disease burden. It's also arguably one of the best studied traits in human disease genetics, and a recent review has pointed out that from 2007 to about 2020, genome-wide association studies for obesity have highlighted over 1,000 different loci associated with various metrics of obesity. And twin studies have shown us that the heritability of obesity is thought to be somewhere between 40 to 70%. So it's a highly polygenic trait, and different metrics of obesity, such as body mass index or BMI, with which most of you are all familiar with, measure different things. So BMI is an overall obesity index, whereas there's a measure that was just referred to in the previous talk, waist to hip ratio, which is a measure of central obesity or body fat distribution, which is also heritable, but in a slightly different way as to overall obesity. But much less is known about the genetic basis of weight change. A lot of obesity genetics have been done on cross-sectional obesity measures, and as Eleanor referred to in her first talk, less is known about how obesity changes across adulthood lifespan. This is quite well studied in childhood BMI, and someone recently referred to a paper where childhood BMI across the ages of a few months to adolescence was measured at different time points, and there was seen different genetic effects were seen at these different time points, but that hasn't yet been done in the adult lifespan. One of the reasons for that is the difficulty of collecting longitudinal data at large scale. And so what we tried to do was to link genetics to primary care electronic health records for longitudinal research. We used the UK Biobank, which I'm sure I don't need to introduce to this audience, but we combined the UK Biobank with the subset that contains primary care records, which has extended follow-up over several decades and contains diverse data types. So there's lab tests, clinical notes, prescriptions, as well as diagnosis information that span several decades of an individual's lifetime. And so in the project that I'm going to talk to you about today, we gathered, cleaned, and performed extensive QC on obesity-related traits from primary care clinics and the UK Biobank centres. We then built and refined trajectory models to define individuals' adiposity trajectories or obesity trajectories over their lifespan. And we then either performed phenotype and disease associations with logistic regressions and time-to-event analyses, or genome-wide associations. And the focus of my talk today will be on this second part, which is the genetic associations of obesity trajectories. So to start with, just a quick overview of what the data looks like. So here, for example, is weight, which is measured longitudinally in about 180,000 individuals with a total of about 1.5 million measurements. As reflected in the UK Biobank, there are slightly more women than men in this data set, with the age at first record being somewhere between somewhere around 60 years. But as you can see, there's quite a lot of heterogeneity in the number of repeat measures, with lots of individuals having well over 50 measurements of BMI or weight in their records. But if you zoom in a bit further, you'll see that the median number of measurements is somewhere around 6 to 7 per individual. And individuals tend to be followed up on average somewhere around 10 to 15 years. On the other hand, if we're looking at a trait like waist circumference, which is a better measure of fat distribution, the data is much more limited. We only have data on about 45,000 individuals with a total of about 120,000 measurements. But the distribution looks quite similar in that they're still measured for the first time around age 60, with fewer repeat measurements and fewer follow-up and less follow-up length on average. And then here's an example of what lifetime patterns of change in obesity traits look like across the population. In blue, I've plotted men, and in red, women, because we know that obesity is a sex-specific trait to some extent. And you can see that the patterns of change in BMI and weight when we look at ages 30 to 70 are nonlinear across the population, whereas patterns of change in waist circumference and waist to hip ratio, which we have measured between ages 40 to 70, are much more linear. And this becomes important when we're thinking about the types of models that we want to use to model obesity trajectories. So to go into a little bit of detail on the types of models, we built mixed effects models for obesity trajectories that either model a linear effect of time or a natural cubic spline effect of time to account for nonlinear effects. So very simply, in these models, obesity is modeled as a combination of a fixed or population-wide and a random or individual level effect, allowing for fixed and random intercepts, fixed and random effects of time, and then adjusted for confounders such as baseline age squared, sex, and other demographic covariates. And then similarly for the natural cubic spline effect, we do the same thing where we allow for fixed and random intercepts, but then we account for nonlinear effects of time via natural cubic spline terms. And so this is what the models look like for a sample of individuals. On the top plots, on the x-axis, I'm showing age in years, and on the y-axis, weight for 5 randomly sampled individuals from the population. And in black dots are the actual observed obesity metrics in the primary care data. In the green line is the linear model fit, and in orange is the natural cubic spline effect fit. And as you can see, for a trait like weight, which I showed you was nonlinear and had several measurements across an individual's lifespan, the nonlinear cubic spline effects model the data better. On the other hand, for a trait like waist circumference, where change across time appears to be more linear, and there are fewer measurements per individual, a linear versus a nonlinear fit don't really make that much of a difference. Okay, so moving on quickly to the genetic effects. The first thing we did was to look at whether we could replicate known loci associated with obesity using the intercept from our mixed effects models. So the phenotype for GWAS here was the fixed plus the random effect, which sort of captures an individual's mean obesity across their lifetime. And in this plot over here, I've colored by different colors loci that were previously reported in the literature, loci that are in LD with reported loci, and in orange, which are a few points that you might be able to see here, loci that I'm calling refined SNPs, which are in LD with reported loci, but are still conditionally independent of these when we adjust for the effects of published BMI loci. And about 3% of the loci that we identify are these so-called refined loci. But we were really interested, and also another way to quantify sort of the power that we get from this intercept GWAS is to look at the chi-squared statistics that we find in our in-house GWAS from these longitudinal measurements compared to the largest meta-analysis out there, which is the giant 2019 release. So in these plots, I'm showing you the chi-squared statistics for genome-wide significant SNPs in either of these two studies. On the x-axis, giant SNPs, and on the y-axis are chi-squared results. And as you can see, we have an effective sample size gain of somewhere between 5% to 30% from using this lifetime averaged obesity as a metric rather than a single cross-sectional measurement. And we think one of the reasons for that is that this lifetime average captures a better, cleaner phenotype than a single cross-sectional measurement would. But what we were really interested in next was the effect of change in BMI or weight over an individual's lifetime. And so we performed slope GWAS, where the phenotype for GWAS was now the coefficient, so the fixed plus random effect associated with time, adjusted for an individual's baseline obesity. And we identified 4 SNPs that were associated with linear obesity change independent of baseline obesity, of which I want to highlight 2 in particular that are in the ApoE locus. So both of these SNPs were associated with both BMI and weight change slopes in all the strata we studied, so female-specific, male-specific, as well as sex combined. And in the ApoE locus, which is a highly pleiotropic locus associated with things such as cholesterol levels, longevity, Alzheimer's disease, and so on, but it is one of the largest lipid loci out there and therefore has a very direct connection to weight change. And finally, just to show you what obesity trajectories look like for carriers of these different weight change alleles, over here is one of the loci one of the SNPs that we identified in the ApoE locus. I've plotted BMI change, weight change, or the 2 body fat distribution measures for which we didn't have power to do GWAS, but we could still look at trajectories of change. And I've plotted on the x-axis time from an individual's first measurement all the way through to about between 10 to 20 years of follow-up, and on the y-axis, modeled weight, BMI, etc. And as you can see, there's clearly different slopes and different patterns of change associated with these, or different patterns of change associated with carriers of these different loci. Here's another example of a SNP that was identified only in women. And so here, if you look at the plots for weight change in women in pink on the left, the intercept differs by very little, but over the course of 20 years, people that are a carrier of the minor allele tend to have about 2 kilograms less in weight than carriers of the major allele, but we don't see that same difference in men, where the SNP seems to only be associated with a different mean or intercept, but not a lifetime trajectory change. Okay. So the linear models were great, but as I've shown you before, nonlinear fits better explain this data than a simple linear model does. And so we went back to the natural cubic spline models, and in order to do sort of genetic analysis here, we decided to cluster individuals defined by these coefficients from the natural cubic spline mixed effects models. So the parameters for clustering were these intercepts or the coefficients from natural cubic spline terms. And so I'm showing you here the results for weight in the sex combined strata, where we identified 5 different patterns of weight change across lifetime. And on the top are samples of individuals within each of these clusters. And on the bottom, I'm showing you either the fitted mean trajectories over time from the first weight measurement up through 20 years, or on the right, observed mean trajectories, which is the population level trajectories for individuals in each of these clusters. And so you can see that we find sort of 2 stable clusters that are either in red, the high stable, or in orange at the bottom, sort of a low stable cluster, and then 3 clusters that either gain weight over the period of measurement or lose weight over period of measurement. And so in order to do genetics on these, we did a very simple binary GWAS where we did probability of belonging to cluster 1 versus not, cluster 2 versus not, and so on. And so we identified different SNPs across the genome that are associated with these weight trajectory clusters. In red and orange are SNPs associated with either that high stable or low stable cluster, which are a lot of which are known obesity SNPs. So in the FTO locus, which is the strongest locus associated with obesity, as well as with other loci associated with BMI, type 2 diabetes, cholesterol, blood pressure, and so on. We once again picked up the ApoE locus associated with individuals in that green cluster that tend to lose weight over time, and it looks quite linear as well. And then we identified a few SNPs in these other clusters that haven't previously been characterized. And so again, just to show you the weight trajectories for individuals at these identified lead variants, there's two different types of SNPs I want to point out. The first set up in the top are SNPs that seem to have an effect on pattern change across lifetime. So carriers of the minor allele show a different pattern of change. For example, they tend to gain weight and then lose it versus carriers of the major allele in these top three plots at the top, versus there are SNPs at the bottom where they only seem to have an effect on individuals' mean or intercept. And so it's the same trajectory patterns at different levels of weight across the lifetime. Okay, so just a quick overview of everything I've shown you today. First, I've shown you why and how we can use primary care obesity records to look at longitudinal changes in things such as BMI and weight across an individual's lifetime. I've shown you mixed effects models to model these trajectories. And then I showed you two sets of GWAS results. The first for linear intercept and slope, where I said that the linear intercept GWAS has higher power than traditional cross-sectional GWAS has in the past. And then second, I showed you that loci associated with slope change show an effect on individuals' trajectories across their lifetime. And then finally, I showed you the genetic architecture of belonging to these different weight trajectory clusters, which seems to be quite polygenic as well. With that, I'd like to acknowledge everyone in the Lindgren group and the Holmes groups, and I'm happy to take any questions that you might have.
Thank you very much, Samvida. That was great. Microphone's coming.
Hi, thank you for the presentation. It was super nice, and I was really impressed by the fact that you had some variants where you had like the decrease in weight over time. And I was wondering if you thought about explanations for that, and whether you rather believe it's intrinsic biology that makes the people lose weight, or that it's like a sort of intervention. They notice they have this thing and they have to be careful, watch out, and go on a diet.
Yeah, that's a really good point, and it brings us to the sort of bias in primary care data to start with, which is that there's informed presence bias. So people that go to the doctor in order for whatever might get their weight measured more frequently if they're already overweight, for example, or they might be on interventions. So yeah, that's definitely something that we're going to look at next to see whether we can characterize why some people lose weight over their lifetime, and if there's something different than just the genetics driving it. I will say, though, that we've already removed individuals that had bariatric surgery records from this data, and so this sort of sharp decline is not being caused by bariatric surgery.
Thanks. Jerome Brinkings, College London. I just wondered, what were your demographic covariates that you put in? And I mentioned that because I think I was really surprised to see the MR result on BMI, and on body fat. It's enormously strong. Sorry, not the BMI for educational attainment on body fat and BMI. It's a very, very strong effect.
Yeah, so we adjusted for sex, smoking status, birth year, and age at which weight was first recorded. And the reason, so I think the birth year adjustment sort of captures these environmental covariates and the sort of growing obesogenic environment. We didn't necessarily look at educational attainment as a covariate. It's worth considering, though.
Yeah. It's very difficult to cross our age range.
Exactly. And we didn't adjust, I should say, we haven't adjusted for most time-varying covariates, so even smoking status we considered as a time-invariant covariate, mostly due to the difficulty of getting longitudinal data from the primary care, for example, on smoking status.
Thank you.
Thanks, really nice talk. Just a quick question, it's correlated to one that you've already kind of alluded to, but have you had the opportunity to look at the correlation between the number of measurements and other health data? Because my intuition would be obviously the number of times you have that data would correlate with some other health related measurements that might somewhat bias your results, or at least preclude kind of being able to extrapolate to the population at large.
Yeah, absolutely. So This, for example, is what I'm calling informed presence bias, which is the number of follow-ups correlates highly with actual baseline BMI or weight, but the length of follow-up doesn't. But then just to sort of, but there's no evidence that these obesity change slopes are associated with the number of follow-ups. And so I agree with you that there is likely a phenotypic bias, but we don't necessarily see that in terms of the trajectories.
Thanks.
Okay, we have a quick question on Zoom from Stefan. What is your time zero in the mixed models?
So time zero is the first time point at which an individual's measurement is obtained. And then we adjust for the age at which that individual's measurement was obtained.
And then another question on Zoom from Clive. How were the clusters identified? Apologies if I missed it.
Oh, no, that's a good question. I didn't go into the details, but we used Gaussian mixed model clustering based on the coefficients from our natural cubic spline models. And then, so because that's a sort of softer clustering where you can get probabilities, we looked to make sure that the clusters were well defined, and most individuals have a probability of 1 of belonging in the cluster they were assigned to.
Well, thank you very much.
Thank you.